So now we will discuss curves in parametric form, or polar form. So that is what we'll present now. So let us take this curve. Question 4. Consider the curve x to the power 2 by 3 plus y to the power 2 by 3 is equal to a to the power 2 by 3. This is a curve. All right. This particular curve is called as an asteroid. I will draw that. The questions are: find the whole length of the above curve. Second, find the area bounded by the curve. All right. So this particular curve is called as an asteroid. Now this has a parametric representation. All right, I'll write here the speciality of this curve. This curve is called as an asteroid. Now, this is a family, is one of the members of the family of hypocycloids. Okay. What is a hypocycloid? It is like this. It is, you take a circle, you take a circle, and then within that circle you take a smaller circle. And make that inner circle roll over the outer circle's inner surface. Okay. And let there be one point on this inner circle M. When the circle rolls on the outer circle, you will get a curve that is formed. So if this is just a side point that I'm writing here just for your reference. So hypocycloids, you can check later. When the circle rolls, the path, this is the path traced by M, is a hypocycloid. All right. Now, when the inner circle radius, let's say, is r, small r, outer circle radius is capital R. If um, it is 1 by 3. Okay, the radius is 1 by 3. Then the ratio of the inner to outer circle radius is 1 by 3. Then it is called as deltoid. I'll show the graphs of it, but this is asteroid is something more important for us. When r by capital R is 1 over 4 times, then it is called as asteroid. Okay, and there are many. As you keep changing, you will get. All right, you can very easily, we can just go to any Wikipedia and type, hypocycloids. You will get full animations of it. See this? I hope you are seeing the animation here. So this is the hypocycloid. This is asteroid. So the ratio small r by capital R is 4. So this is the asteroid. And there are many. So these are various forms. This is deltoid. Ratio is 1 by 3. Or, capital R to smaller ratio is 3. Capital R to smaller ratio is 4. Capital R to smaller ratio is 5. Like that. So you get various forms of curves like this. We are interested in this one. Now, how to plot? Now, this has one parametric representation. This is the curve. Now, parametric representation of an asteroid. X to the power 2 by 3 plus y to the power 2 by 3 is equal to a to the power 2 by 3. The parametric representation will be x is equal to a cos cube theta, y is equal to a sine cube theta. When you substitute this, we get a to the power 2 by 3 times cos square theta plus a to the power 2 by 3 times sine square theta. When you add up, you will get a to the power 2 by 3. So this is the parametric representation of an asteroid. So now let us trace the curve. You will not have this option in the exam of trying to trace this curve by your own methods, by using the grapher. You will have to trace the curve by hand. So let us trace this curve by hand. So now let us move to the solution. So x square to the x to the power 2 by 3, y to the power 2 by 3 is equal to a to the power 2 by 3. When you just see this, very first thing is this is x square cube root plus y square cube root is equal to a to the power 2 by 3. So x can take positive or negative values, y can also take positive or negative values. Very simple. Now you replace x by minus x. When we replace x by minus x, the equation does not change, which means the graph is symmetric about the y-axis. When we replace y by minus y, again the equation does not change. So graph is symmetric about the x-axis. Now we can replace x and y simultaneously by minus x and minus y. Again, the graph doesn't, the equation does not change. So graph is symmetrical about the origin. So immediately we can know. Now region in which curve lies. So for y square, y to exist, this is important. So for this, y square will be a to the power 2 by 3 minus x to the power 2 by 3 whole cube. So now for y to exist, for y to be real, the right hand side has to be positive, which means this is a whole cube. So the sign depends on the inner terms. So a square, a to the power 2 by 3 minus x to the power 2 by 3 has to be greater than 0. Okay, this has to be greater than 0, which basically means it is like a square minus x square has to be greater than 0, which um, basically means x, we see here, if x is positive, it has to be less than a, and if x is negative, it has to be greater than minus a. Okay, so the curve lies between, therefore the curve lies between minus a and a along the x-axis. Similarly we can do with the y-axis. You take x square is equal to a to the power 2 by 3 minus y to the power 2 by 3 whole cube, and you will get that. So we get this, and it lies between, y lies between minus a and a. It takes the value a. And now where does the curve cut the x-axis? Put y equal to 0. We get x equal to plus a and x equal to minus a. And put so the curve cuts at x equal to a and x equal to minus a, and it cuts at y equal to a and y equal to minus a. It cuts the y-axis. Now in between, how will the curve look like? Okay. How will the curve look in between? Now, just between 0 and a, x equal to 0 and a, we need to see how does the curve look. So we'll have to differentiate and see how the curves look. So let us differentiate. Now differentiating, x to the power 2 by 3 plus y to the power 2 by 3 is equal to a to the power 2 by 3. So when we differentiate this, we get 2 by 3 x to the power minus 1 by 3 plus 2 by 3 y to the power minus 1 by 3 dy by dx equal to 0. So 2 by 3 goes, and we have dy by dx is equal to, take this to the left hand side, minus of x over y to the power minus 1 by 3. or this is same as y by x to the power 1 by 3. So in the first quadrant, this is x and y both are positive. So dy by dx will be negative. So it's a decreasing function. That is sure, because at x equal to 0, it is a, and x equal to a, the value of the function is 0. So you will get a curve like this. Now, whether it is a concave curve or convex curve, that is what we have to look for. So we have to differentiate it twice. Okay. So let us do that. Maybe we can differentiate this, or we can check how does the slope change from one point to another. From now, as x tends to 0, first derivative test only we can do. As x tends to 0, okay, the dy by dx value, y will be tending to a, because as x tends to 0, the function value is approaching a. All right, this we just found here. All right, so numerator is a, denominator is approaching to 0, so it will go to infinity, but with a minus sign. So that means the slope is minus infinity. And as x tends to a minus, what happens to dy by dx? Dy by dx will tend to, as x is approaching a, dy by dx, what happens to dy by dx? Y is becoming 0. X is approaching a, so this ratio becomes 0. So what is happening? The slope is changing continuously from minus infinity to 0, which means dy by dx is increasing from it is moving from negative real number line to positive real number line, the values. So this is increasing minus infinity to 0. Therefore, in this interval, okay, for x lying between 0 to a, d square y by dx square will be greater than 0, as dy by dx is increasing. Okay, these are the concepts of basic application of derivatives, which we will use for plotting the curve. So now we have got that the second derivative is positive, so it is convex, concave upwards. So here I draw the curve, the tangent. So y-axis will be tangent at a, and x-axis will be tangent, at y-axis will be tangent at 0 comma a, x-axis will be tangent at a comma 0. So this is the curve. Similarly, now because of symmetry, it is symmetric about y-axis. So we can draw this. It is symmetric about y-axis. Okay, I'll put it a little away. That is the point A. Okay, and now it is symmetric about the x-axis, so it will be a mirror image. So this is how I have traced the curve. Now I have taken so much time to explain, but you have just 1 minute to trace out this curve in the exam. So you should be very, very fast. Whatever I have done here in rough calculation, very fast, you should be able to do it. Now this is the asteroid, and as I had shown you here, see, this is the asteroid. This is the curve. Okay. Now our question, now we'll do it first by Cartesian method, and then we'll go by parametric method. Now let us go by Cartesian method. First, I want to find the length of this curve. So 0 to a, I want to find the length of this curve. If I multiply the whole curve I want, so if I find this length, then multiplied by 4, I can find the entire length of the curve. So finding the length of the curve. Okay. So S, this is in the first quadrant. First I'll do the branch in the first quadrant. So S is integral ds, which is integral 0 to a under root of 1 plus dy by dx whole to the power a whole square times dx. This what it is. So now dy by dx for this curve we have found here. Dy by dx is this. So now let us solve this. How to do this? Dy by dx is y upon x to the power 1 by 3 with a minus sign. So what is 1 plus dy by dx whole square? So that we need to see now. So 1 plus dy by dx the whole square is equal to 1 plus. So y upon x. So we get y to the power 2 by 3 by x to the power 2 by 3. So from here we get this is x to the power 2 by 3 plus y to the power 2 by 3 by x to the power 2 by 3. Now x to the power 2 by 3 plus y to the power 2 by 3 is a to the power 2 by 3 from the equation of the curve. Okay. And denominator is x to the power 2 by 3. So it simplifies in a simple manner. So therefore S is integral 0 to a under root of a to the power 2 by 3 by x to the power 2 by 3 dx. Now when I take the under root, I get a to the power 1 by 3 by x to the power 1 by 3. I do not get a modulus. Why? Usually, if I do under root of x square, I should get modulus of x. I do not get a modulus because x is already positive. It lies between 0 and a. We are integrating within that limits. If it was minus a to a, then under root of this, we have to write it with a minus sign here. So that caution we have to take. That's why best is always first quadrant. If you have to find a length of the curve or area of the curve, first quadrant we solve and then multiply by 2 or 3 or 4 as it is required. Now this is very simple. It is a to the power 1 by 3 comes out. This is x to the power minus 1 by 3 plus 1. That is x to the power 2 by 3. So a to the power 1 by 3 times x to the power 2 by 3 by 2 by 3, 0 to a. So a to the power 1 by 3 times a to the power 2 by 3 minus 0 by 2 by 3. So we get 3 upon 2 a to the power 1 by 3 times a to the power 2 by 3 is a. So this is one portion of the length of this curve. So therefore the total length of this curve, the total or whole length of the curve is 4s, 4 times 3 by 2a, which is 6a. This is the total length of this curve. So this curve was in the first quadrant that we found. Clear? So it is a matter of just understanding. It is important if we can remember this curve, it is best, because this is one of the standard curves. It is not a new curve. It's a age-old curve, very standard curve. We can remember this curve. That's right. Now, how to find the area? So finding the length of the curve is done. Finding the area, I want you all to solve and tell me. I'll copy the graph. Yeah. So find the area bounded by the curve. You can put it in the chat. If you're not getting the idea, just let me know in chat. These are the options. How many of you got an idea of solving this and you are solving it? Raise hands. Raise your hand. No one? Okay. How many of you did not get an idea of how to solve the integral? Raise your hands again. Okay. How about others? I have 7 hand raises. Other 6, 8 hand raises. Okay. All right. Just look at this. You can put your hands down. Yeah, some of you got an idea. You are trying it. Try that. No problem. Okay. Others, look at this. I will find area in of the first quadrant only. So I will take an elemental strip here. Elemental strip of length, dx, and this is y. So the area bounded by the curve in the first quadrant curve in the first quadrant between the axis is, let's say a1, is integral 0 to a y dx. Okay, integral 0 to a y dx, f of x dx. Now y is, x to the power 2 by 3 plus y to the power 2 by 3 is equal to a to the power 2 by 3, which implies y to the power 2 by 3 is a to the power 2 by 3 minus x to the power 2 by 3, and y will be a to the power 2 by 3 minus x to the power 2 by 3 whole raised to the power 3 upon 2. Therefore, this area A will be integral 0 to a to the power 2 by 3 minus x to the power 2 by 3 whole to the power 3 by 2 dx. Okay. Now, this is a this is the integral. How to solve this particular integral? There's no standard way. You have to use substitution. Best substitution is your parametric substitution. Substitute x is equal to a, substitute x is equal to a cos cube theta. X is equal to a cos cube theta. When we substitute that, see what happens. Dx is a into 3 cos square theta into minus sine theta d theta. And let's look at the limits. X and theta. When x is equal to 0, theta, so cos cube theta will be 0, which means cos theta is 0, which means theta is pi by 2. And when x is equal to a, theta, cos cube theta will be 1. So cos theta will be 1, which means theta is 0. So that's what you get. Therefore, a1 will be integral 0 to a to the power 2 by 3 minus a to the power 2 by 3 cos square theta, because cos cube to the power 2 by 3 will be cos square theta to the power 3 by 2 times, oh, I'm sorry, the limits will not be 0 to a. I'll write the limits at the end, times minus 3a cos square theta sine theta d theta. The limits will be from pi by 2 to 0. When x is 0, theta is pi by 2. When x is equal to a, theta is 0. This will be the limits. Now, we pull out a to the power 2 by 3 outside. A to the power 2 by 3 raised to the power 3 by 2. So you get a. And 1 minus cos square theta becomes sine square theta. Sine square theta to the power 3 upon 2. So we get sine cube theta times minus 3a cos square theta sine theta d theta. So from pi by 2 to 0. Now we take the minus sign. We remove the minus sign by interchanging the limits. Integral a to b f of x dx is equal to minus integral b to a f of x dx. So the limits can, so when you change the limit, the negative sign goes away. And then we have 3a square sine to the power 4 theta to cos square theta d theta. Now this is 3 times a square. Now apply the Valley's formula. We can apply the Valley's formula. What we get? We start with, this is 4 and 2. So 4 minus 1, 3. Then 3 minus 2 is 1. You end there. 2 minus 1 is 1 divided by 4 plus 2 is 6. It starts with 6, 4, 2 multiplied by pi by 2. So 3 cancels once. So 3 pi a square upon 4 into 4, 16 into 2, 32. So this is the area bounded in the first quadrant. So the total area bounded by the curve. So what we found by this integral is this area. Okay. So now the total area will be 4 times of this area, because the same reflection is there in the other 3 quadrants of the same area. So it's 4 times A1. So 4 times 3 pi A square upon 32. This is 3 pi A square upon 8. So this is the correct option. This is the correct option. So although this is a parametric curve, we did it by, the normal Cartesian integral, but we used a substitution. Now, why not use the parametric equation directly? Let us do that. Let us do that right now. Alternative, using parametric integration. Okay. So given equation is x is equal to a cos cube theta, y is equal to a sine cube theta. So when x is equal to when theta equal to 0, x will be x will be a, and when and y will be 0. That means a comma 0. And when theta equal to pi by 2, so theta can be treated as the angle that, so I'll draw the curve again. Yeah. So this parameter represents the, suppose there is a point. Of course, many times it may be difficult to identify the parameter. Suppose there's a point on the curve, and you draw a line joining the origin to the curve. This angle is theta. So when theta is 0, you get the point, x coordinate of the point as a, y coordinate of the point as 0. So you get this as a comma 0. When theta equal to pi by 2, we get x as 0 and y is equal to a. So we get this point, and theta is pi by 2. Okay, there's a parametric representation. Now finding the length of the curve by parametric representation. Length of the curve. All right, the total length of this curve will be 4 times the length of the curve in the first quadrant. 4 into length of the curve in first quadrant. Okay. So now let's begin. So in parametric form, integral, S1 itself is integral ds, which is integral under root of dx square plus dy square, which is integral dx by d theta. Because our parameter is in terms of theta, we can write it as t also, doesn't matter, cos t sine t. Parameter is theta. D theta 0 to pi by 2. Theta varies from 0 to pi by 2 as we have observed. So dx by d theta is, so we'll write here dx by d theta is 3a cos square theta into minus sine theta, and dy by d theta is 3a sine square theta into cos theta. So now when we square them and add, we'll get 9a square times cos power 4 theta sine square theta plus 9a square times sine power 4 theta cos square theta d theta. Pull out 9a square outside the uh, square root. So you'll get 3a integral 0 to pi by 2. We have under root, take cos square theta sine square theta common. Then we'll get cos square theta plus sine square theta. So we get 3a times integral 0 to pi by 2 under root of cos square theta sine theta, which will be cos theta sine, sorry, cos theta sine theta. Without the modulus, why? Because in the first quadrant, that is when theta lies between 0 to pi by 2, both cos and sine are positive. They are positive. So that's what we get here. Okay, so this is what we get. And then let us integrate. Derivative of sine theta is cos theta. So we can write this as the antiderivative as sine square theta upon 2. Derivative will be 2 sine theta cos theta by 2. So you get sine theta cos theta. 0 to pi by 2. So we get 3a into 1 upon 2 minus 0. So 3a upon 2. This is S1, the length of the curve in the first quadrant. Therefore, S is 4 times S1, which is 4 times 3a upon 2, which is 6a. All right. So we have done it with parametric method. The same equation. Let me see. Here. This third formula is the parametric formula. Integral alpha to beta under root dx by dt whole square plus dy by dt whole square of dt. So using this, we have done this. In parametric method. How to do it with integral form? In parametric form, the substitution is all very, very simple. So finding area bounded by the curve. My parametric method. So A is 4 times A1, 4 times the area in the first quadrant. So area in the first quadrant is integral y dx. You write like this. Now x of course is varying from 0 to a, but y we can write in terms of theta. X also we can write in terms of theta. So dx will be dx upon d theta times d theta. So we have this x equal to a cos cube theta, and y is equal to a sine cube theta. So when we are substituting in terms of theta again, x and theta, when x equal to 0, theta equal to pi by 2, and when x equal to a, theta is 0. So what we get is integral pi by 2 to 0 y. Y is a sine cube theta into dy by dx is 3a cos square theta into minus sine theta d theta. So 3a square comes out, and the minus sign can be removed by interchanging the limits of integration. And we have sine to the power 4 theta cos square theta, the same integral which we got by substitution. So by Valley's formula, we get 3 into 1 times 1 by 6 into 4 into 2 times pi by 2 using Valley's formula. So 3 pi a square upon 32. Therefore, a is 4a1, which is 3 pi a square upon 8. So is this clear? So I have done by two methods, just using, of course, by Cartesian method also, we are indirectly using parametric method because we are using that substitution. But if we directly do by parametric methods, things are very, very simple. You get the integrals very easily, but very important, Valley's formula you have to remember. So whatever we are doing has a use some way or the other. That's why you cannot omit. Okay, Valley's formula, I'll leave it. What is that? When you learn that, in other place, it will be useful. So calculus is like that. Whatever we have learned is useful. Point of inflection is useful. Point, in curve tracing, we have used so many logical points. If we learn that and remember that, we'll be able to trace the curve very easily. Otherwise, just this equation is given, we won't know to trace the curve, nor will we know how to find the limits of integration. That is why curve tracing is extremely important. All right, I'll proceed to the next problem. Next problem, problem number 5. It is on cycloid. As the name suggests, Previously, in hypocycloid, we had one circle revolving, rotating on the circumference of the other circle. In cycloid, it is different. Just a second. Just a second. Okay. Now you have flat surface in a cycloid and you choose one point, say M, and as this rolls over this flat, the path traced out by this point M, as the cycle rolls, the wheel of the cycle rolls, the path traced out by this curve is called as the cycloid. Like that. Okay. Let us see this. So I hope you're able to see this, how this is being traced. So this is a cycloid. Now, the equation of the cycloid is represented parametrically. X is equal to a times theta minus sine theta. Y is equal to a times 1 minus cos theta. So when theta equal to 0, x is 0 and y is 0. So this is this point. So when we plot the curve, so this is the curve. Theta equal to 0, x is 0, this is x, this is y. When theta equal to pi by 2 or theta equal to pi, you will get this. So this is when x is 0 and the maximum value occurs when this is maximum. That means cos becomes -1. Cos becomes -1 at pi. So this becomes 2a. This length is 2a. At when theta is pi. When theta becomes pi, you get pi minus 0 times a. So this is pi times a. Now here this becomes 2 pi times a. This is 3 pi times a. This is 4 pi times a. This is x and this is y. So theta changes from 0 to pi here. Theta ranges from 0 to pi in this case. And from here to here, it varies from 0 to 2 pi. Okay, this is the how parameter is changing. So we have to be careful when we are doing parametric integration. It is very important to know how theta is varying with what value. Now the question that we need to find for this cycloid, the question, the curve will not be given, just this curve will be given. X is equal to a into theta minus sine theta, comma y is equal to a into 1 minus cos theta. Just this much will be given. And the question is, first part, find the length of the arc of the cycloid. Second, find the area included between an arc of the cycloid and its base. So we just need one arc length. So from point 0 to 2 pi a, and we need to find the area in this region, this shaded portion. That's all. This is the question. So I want you all to solve now. It is parametric form. Use the parametric equation and solve. It is not a difficult one. Very easily you can solve. I'll give 5 minutes, 3 minutes time. Integral is easy, at least the length of the arc. How many of you got arc length integral? Please raise your hand. No, the answer given wrong. Maybe some error in the integral. Okay, I will solve. Look at the solution. You can try it out again later. The arc length S integral ds, which is integral under root dx by d theta the whole square plus dy upon d theta the whole square d theta. Theta varies from 0 to 2 pi. Theta varies from 0 to 2 pi for one full arc length. So now 0 to 2 pi. So let us write what is x is a times theta minus sine theta. So dx upon d theta is a times 1 minus cos theta. Now y is a times 1 minus cos theta. So dy upon d theta is a times derivative of 1 is 0. Derivative of cos theta is minus sine theta with a minus sign. So I get plus sine theta. So we have this as under root of dx by d theta whole square, that is a square into 1 minus cos theta the whole square plus a square sine square theta d theta. So this is equal to integral 0 to 2 pi. Take a outside. We have 1 minus 2 cos theta plus cos square theta plus sine square theta d theta. So a still remains outside, 0 to 2 pi. We get 2 cos theta plus sine cos square theta plus sine square theta is 1. 1 plus 1 is 2. So 2 into 1 minus cos theta under root d theta. A times 0 to 2 pi. This is 2 under root of 2 into 2 sine square theta by 2. Now theta varies from 0 to 2 pi. So theta by 2 will lie between 0 and pi, and sine of a value between 0 and pi is positive. So when you take when you apply the under root, you don't have to use mod. You can straight away write this as 2 sine theta by 2 d theta integral 0 to 2 pi. So this is 2a. Derivative of integral of sine theta is minus cos theta upon 2 by half by the coefficient from 0 to 2 pi. So take the minus sign out, so minus 4a times cos of 2 pi upon 2 is cos pi minus cos of 0 upon 2 is cos 0. 4a minus 1 minus 1. So this is 8a. So the length of the arc is 8a. So please check wherever a mistake has happened in the integral. So length is 8a. Arc length is 8a of the cycloid. Now area included between the arc and the cycloid. Parametric. So I hope everybody got this integral, the first part, arc length. Now the second part, area. It's integral y dx. Now y is a into 1 minus cos theta. Dx is dx upon d theta into d theta. So that is a times 1 minus cos theta d theta. Very simple. Theta varies from 0 to 2 pi. So we have a square into 1 minus cos theta, the whole square, 0 to 2 pi. So of course we can do this. 1 plus cos square theta minus 2 cos theta d theta. Cos square theta can be written as 1 plus cos 2 theta upon 2 minus 2 cos theta. It's just a matter of solving the integral. So this is integral 0 to 2 pi. 1 plus 1 by 2 is 3 by 2. Plus cos 2 theta upon 2 minus 2 cos theta d theta. Now 2 theta, if theta varies from 0 to 2 pi, cos 2 theta will vary from 0 to 4 pi. Now remember, in integral, the area above the x-axis, area below the x-axis will get cancelled. So the next two integrals get cancelled. You know, this one and this one will become 0. You can integrate and substitute, but I'm directly telling by this. Okay, I'll write one more step for your understanding. Directly by seeing the integral, I am telling that these two integrals will be 0. You can evaluate. Okay. So for multiple, you can use one of the properties, and also just by the concept of integral over, I explained how sine theta integral from 0 to 2 pi is 0. So similarly, cos theta from 0 to 2 pi will be 0. Okay, so we get a square into 3 by 2 into theta. Substitute the limit, 2 pi minus 0. So we get 3 pi a square as the area. Area is 3 pi a square square units. Okay. So yesterday we did areas with Cartesian coordinates. So today, in today's class, we did area with parametric parametric representation of the curve and how to integrate using parametric form. One more is left, polar form, very, very useful, extremely useful. So curves in polar coordinates. Okay, we have these curves. Equation of a circle. Equation of a circle with center at pole O and radius A is in polar coordinates r is equal to A. This is the equation. We can see this. This is the initial axis. This is the pole, and r is equal to A. A is the radius. So r equal to A gives by default the equation of the circle in polar coordinates. Okay. Now, second one, these are some important curves in polar coordinates. R is equal to 2a cos theta. What will this give? When theta equal to 0, we get R is equal to 2a. When theta equal to pi, when theta is equal to pi, we get minus, no, R cannot take a negative value. When theta equal to pi by 2, when theta equal to pi by 2, see, R cannot take a negative value. You should remember this. So for this equation to be valid, cos theta has to be positive. Cos theta is positive. How to trace this curve? We have to see. Cos theta must be greater than or equal to 0, which means theta has to lie between pi by 2 and minus pi by 2 and pi by 2. Only then it is possible. Okay. It cannot lie in pi by 2 to 3 pi by 2 where cos is negative. So let us trace. What will this be? This will also be a circle. Let us trace this. This will be a circle whose diameter is 2a. This is the initial line. This is the pole O. This is the value of R, and this is theta. Okay, so the point is R comma theta. Oh. R comma theta. So R is 2a cos theta comma theta. So substitute. When theta is equal to 0, theta equal to 0, R value will be 2a. So this point will be here. The first point will be here. Okay, let this be the point M. The second point, when theta is, as theta keeps changing, let's say it comes here, I think it will be 45 degrees angle. No, it will be, so R value will keep changing and R becomes 0 when theta is pi by 2. As theta, this value keeps changing to pi by 2. It goes to pi by 2, the value of R is 0. And then here from minus pi by 2 to 0, 0 to pi by 2, this is the way theta will vary. So this curve, it's an important curve. R is equal to 2a cos theta. R equal to 2a cos theta is a circle um, whose center, circle with center at R equal to a. All right, distance of R equal to a and theta equal to 0. And radius is equal to a. Radius is equal to a. So this is the another equation of a circle. This is in polar form, R equal to 2a cos theta. Next, another important equation, very important form, is cardioid. Cardioid, as the name suggests, the curve will be in the shape of a heart. I'll trace the curve. There are 4 types of equation here, but let us trace these 4. First one, it is R is equal to a into 1 plus cos theta. In this, the cardioid, the curve will be like this. When theta equal to 0, the value of the cardioid, value of R is 2a. So this point will be 2a R comma 0, 2a comma 0. This is theta equal to 0 line. This is theta equal to pi by 2 line. When theta equal to pi by 2, so we get R is equal to a. When theta equal to minus pi by 2, again R is equal to a. So you get, this is theta comma pi by 2. This part is theta equal to minus pi by 2. Here this line will be theta equal to pi. And theta can go negative values also. So however, R will always be positive. 1 plus cos theta will always remain positive. So for all values of theta, this exists from minus pi. Okay, we can write minus pi to pi. Theta below, at the bottom, it will be minus pi. If you're approaching the angle like this, it is minus pi. If you're approaching the angle this way, it is pi. So this is R equal to a times 1 plus cos theta. This is a cardioid. So this is the equation. This is the shape of the curve. This is the first type. The second type uh, is r is equal to a into 1 minus cos theta. So when is cos theta negative? When theta is when cos theta is -1, when theta is equal to pi. So r will be 2a when theta is equal to pi. So the shape of the graph will be a mirror reflection of what we have seen here. So here in polar form, this is theta equal to 0 line. This is theta equal to pi line. This is, or theta equal to minus pi, theta equal to pi by 2, theta equal to minus pi by 2. This is the pole. The cardioid shape will be like this. Okay, I have not drawn a perfect shape, but this is the shape of the cardioid. Next, we have two more cases. R is equal to A into 1 plus sine theta. So you can guess what the shape will be. When theta equal to 0, R is equal to A. When theta equal to pi, R is equal to A. When theta equal to pi by 2, R is equal to 2A, this distance. And when theta is equal to 3 pi by 2, R is 0. So here. So the cardioid will be a curve like this. In this particular case, this is a comma 0. This is a comma pi. This point is 2a comma pi by 2, r comma theta point. And this point, of course, is the pole, and this point is also 0 comma 3 pi by 2 or 0 comma minus pi by 2. Same. So better to take minus pi by 2. That's the same. Now we'll see the integrals. Interestingly, in GATE, we have got questions on cardioid. It is not, they have not mentioned it as cardioid, but this is the curve. In some previous papers, we have got questions on cardioid. I should not write this as X and Y. It gives a wrong impression. This is theta equal to 0, theta equal to pi by 2, theta equal to pi, theta equal to minus pi, theta equal to minus pi by 2. Same here, theta equal to 0, theta equal to pi by 2, theta equal to pi. The same line can be theta equal to minus pi, theta equal to minus pi by 2. So the fourth one is r is equal to A into 1 minus sine theta. So when theta is equal to minus pi by 2, you get sine theta as minus 1. So R will be equal to 2A. And when theta equal to 0 and theta equal to pi or minus pi, R will be equal to A. And when theta equal to pi by 2, you get R as 0. So this will be the shape of the curve. So there are 4 cardioids. R is equal to A into 1 plus cos theta. R is equal to A into 1 minus cos theta. R is equal to A into 1 plus sine theta. R is equal to A into 1 minus sine theta. So 4 cardioids, 2 circles, R equal to A, R equal to 2A cos theta. Okay. Now questions on this. These are previous questions from GATE. Today we have done. All right. On this section, the first question, curves in polar coordinates. First question. Find the perimeter and the area enclosed by the curve R is equal to 2A cos theta. What is the answer? Tell me the answer straight away. Think and tell me the answer. If you have heard me clearly, answer, you will answer this in 10 seconds. Please type in the answer. What is R equal to 2A cos theta? Anyone? What is R equal to 2A cos theta? You can unmute yourself and speak.
Sir, circle with diameter 2a.
Very good. Excellent. Circle with diameter 2A. So, good. So what is the answer now? What is the perimeter of that circle? Perimeter of a circle of radius A or radius R is 2 pi R, right? So 2 pi A will be the perimeter. What is the area enclosed? Pi A square. You don't have to do anything. Just that if you know the polar representation, what it is, you can directly write the answer. This is the initial line, theta equal to 0. Okay. This is the circle pole. This is 2A comma 0. 0 comma pi by 2. Very simple. You don't have to do anything. Answer perimeter is perimeter is 2 pi A. Area is equal to pi A square, because this is curve is, it is a circle, it is a circle of radius A. Solved. Problem is solved. However, we'll do an integral in polar coordinates. It is important. Okay. Integral in polar coordinates. we should remember the perimeter ds square in polar coordinates is r square plus r square d theta square. Okay, or r d theta square. So r d theta the whole square. So we should remember this. Now, if we have to integrate, this is r, keeps changing, and this is theta. Theta varies from minus pi by 2 to pi by 2. See the curve. This line is theta equal to minus pi by 2. This vertical line is theta equal to pi by 2. It's polar coordinate. It is not Cartesian coordinate. Okay. So if I have to find the perimeter, I have to integrate from theta equal to minus pi by 2 to theta equal to pi by 2. So perimeter S is integral ds, which is integral under root of r square plus r square d theta square. Now I have to, sorry, this dr square plus r square d theta square. It's not r square, dr square plus r square d theta square. Now I have to integrate with respect to theta. So I pull out theta. So I get dr by d theta square plus r square under root d theta. Theta varies from minus pi by 2 to pi by 2. This is the perimeter. Okay. So what we get is dr, r is 2a cos theta. So let us substitute minus pi by 2 to pi by 2 under root dr by d theta is 2 minus 2a sine theta the whole square. So minus 2a sine theta whole square plus 2a cos theta the whole square d theta. Okay. So this is 2a comes out common. Integral minus pi by 2 to pi by 2 sine square theta plus cos square theta is 1. So 2a to pi by 2 minus of minus pi by 2 is pi. So 2 pi a is the perimeter. Correct? This is how we do an integral. Second integral. For the area. How do we find the area? Area of the sector. So this is the initial line. For finding the area, we take a strip. We'll take a big strip. Actually, it should be very small, but to illustrate it, I am taking. This is r d theta. Okay. Now integrate this strip. So area enclosed by the curve is area is half r square d theta is this area of this particular sector. Now all such sectors, when theta varies from minus pi by 2 to pi by 2, this is the line. Theta varies from minus pi by 2 to pi by 2. Okay. See, when the point moves, r theta is minus pi by 2 here, increases, goes to 0, goes to and comes to pi by 2 theta, the angle that the point makes with the initial line. So theta varies from minus pi by 2 to pi by 2. So we get A is equal to integral minus pi by 2 to pi by 2 half r is 2a cos theta. So 4a square cos square theta d theta. Okay. So we get, because it is an even function, so we can write this is already 2a square outside. So multiplied by 2 from 0 to pi by 2 cos square theta d theta. Now this integral, okay, this is a standard integral. I is equal to integral 0 to pi by 2 cos square theta d theta. This I is same as integral 0 to pi by 2 cos square pi by 2 minus theta d theta. It's a standard integral. So 0 to pi by 2 sine square theta d theta. I plus I is 0 to pi by 2 cos square theta plus sine square theta d theta, adding the two integrals. Integral 1 d theta, so that is d theta pi by 2. So I is equal to pi by 4. This is a standard integral. So you get 4a square into pi by 4, which is pi a square. So this is the area of the circle, which we don't have to do all this. Just if we know that this curve represents a circle of radius a, you already solved it. It is just a 10-second question. But I'm showing how you can do the integral. For a known curves, if you do the integral, we can cross-check the values, whether we are getting the right answer or wrong answer, and how to find the area. It is a good practice for finding, for Cartesian, sorry, for polar curves and polar coordinates. Okay, let's do another one. Question 2. This is another gate question. Gate 2006. This question came. Find the area. Of course, I'm writing it as a question. It was an objective question. Find the area common to the curves R is equal to A and R is equal to 2A cos theta. So think about it and draw the curves first in your paper. First, I'll just give you 30 seconds. Just draw 30 seconds to 1 minute. Draw the curves on the paper. Okay. I presume you have drawn the curves. So first one, R equal to A. Let us plot. Both are circles. Both are circles of radius A. No, both are circles of radius A. Just that for the first circle, R equal to A, the pole is at the center of the circle. Okay, I'm not able to adjust. Hmm. Oh, oh. Okay. All right. Okay, this is the uh, pole and this is the initial line. Now, when the circles intersect, what is common? R and theta should be common. So the distance from O will be the same for this blue circle and for the green circle. The blue circle is, of course, R is equal to A, and the green circle is R is equal to 2A cos theta. Okay. So now, at this point, R and theta should be the same. So these are the points of intersection, and this is common to the curve. So let us see how we can do this. So finding the point of intersection. Points of intersection. The first one. So equate R. Equate the equate the equations of the two curves. So A is equal to 2A cos theta, which implies cos theta is equal to half. Cos theta is equal to half, which implies theta is equal to 60 degrees, which is pi upon 3. So R is equal to A. And so the points of intersection are um, R comma theta equal to A comma plus pi by 3 and A comma minus pi by 3. Cos of minus theta is also cos theta. So these angles is pi by 3 and then, sorry, this one minus pi by 3. So now find the area common to these circles is this common area. So how to do? So of course, this is symmetric. These curves are symmetric. So we have, I'll expand it. Okay, just look at this. We can just find the upper portion. This portion and then this portion. These two portions we find, we get the area. So let us do. So required area, we can mark these points as O, A, B, O, A, B, and again O. So required area. So I'll write here the required area is equal to twice into area OABO, this closed within the curves, which is equal to twice of integral theta equal to 0 to pi by 3 r square half r square d theta plus integral theta equal to pi by 3 to pi by 2 half r square d theta. Why did I do this? You see here, from 0 to pi by 3, the curve will be this blue curve. So that is one function r. And from pi by 3 to pi by 2, it will be the green curve. Okay, when theta varies from pi by 3 to pi by 2, it will vary along this green curve. So the first curve will be the blue curve, that is A. So we get 2 integral theta equal to 0 to pi by 3 half r is A square d theta. Straightforward. plus integral pi by 3 to pi by 2 half r. The green part is 2a cos theta. So this is twice of a square by 2 times. This is pi by 3 minus 0. Plus this is 2a square and integral cos square theta. Of course, we'll have to do 1 plus cos 2 theta upon 2 integral pi by 3 to pi by 2. So this part is pi a square upon 3 plus this is 2 cancels again 2a square theta plus sine 2 theta upon 2 integral from pi by 3 to pi by 2. So pi by 3 a square plus 2a square pi by 2 minus pi by 3, the first part, plus half sine pi is 0 minus sine 2 pi by 3, that is sine 120, is same as sine 60 is 3 pi by minus root 3 by 2. So we get pi by 6 into 2, so pi by 3. So pi by 2 pi by 3 a square. This is what we get here. Pi by 6 into 2 pi by 3 a square plus pi by 3 a square is 2 pi by 3 a square. Minus root 3 upon 2 a square. So 2 pi by 3 minus root 3 upon 2 a square. Answer given is in numericals, numerical coefficient. This is, I'll just check. Two times pi divided by 3 minus no minus root 3 upon 2. Just a second. Answer given is this one. We have multiplied it by 2. So 0.866 is minus root 3 by 2, and let's see 2 pi by 3, what will that be? 2 into pi divided by 3. 2 into pi divided by 3. 2.094 minus 0.866. So 1.228, correct. So 1.228 a square. This is the answer given in GATE. All right, area bounded by the two curves. So, okay, so I'll stop here now.